This is Shashikant from Electrical Engineering Department, University Lucknow. Today, I am going to discuss about the steady-state behavior of queuing model and networks of queues. The theory of probabilities is at bottom nothing but common sense reduced to calculus. It enables us to appreciate with exactness that which accurate minds feel with a sort of instinct for which often times they are unable to account. Here we will demonstrate how to analyze the behavior of queuing model using the theoretical framework about random processes. We formulated the simplest queuing model is the is chosen for this purpose. Although extremely simple, the M/1 model is sufficient for demonstrating the standard procedure of deriving various performance metrics of a queuing system based on the theoretical framework established for describing the different kind of processes. In addition, the M/M1 model reveals many basic facts of a wide range of more complex queuing model. The analysis of M/M1 queuing model can be carried out by applying the limiting state probability. Here we are going to take an example of the birth-death chain to obtain the different results. So first of all, we are going to discuss about the example related to birth-death chains. Birth-death chains are the limiting state probabilities as repeated below for the initial state probability, initial state probability and limiting state probability together with the normalization condition for the state probabilities. Another statement we need to make is that we will use a generic random variable is used to denote the random inter-arrival times between successive arrivals. These choices are well justified under the assumption of IIT we discussed earlier. The M(m)(1) model represents a queuing system that is characterized as follows. First is the Markov arrival process, which implies the Poisson distribution for the number of customers in the system and exponential distribution for the inter-arrival times. Markov service pattern, which implies that service times obey the exponential distribution. Next, single server for all customers. Next, infinite system storage capacity. Infinite system storage capacity. Next, first come first served policy. Then the generic birth date model can be simplified for the M(m)(1 model with the following arrival and departure rates. Lambda n is equal to n for all n 0 to 1, mu n is equal to mu for all n 1, 2 and so on. This can be simplified where represents the load intensity is the load intensity. Now we will proceed to drive all major performance matrices of M/M/1 queues based on the equations. Now the utilization U of an M/M/1 queuing system can be obtained with the initial state probability initial state probability, which defines the relative portion of the time when the system is empty and server is ideal. It is simply U is equal to 1 minus yes, the system throughput x naught can be defined as the mu p lambda. This conclusion can also be obtained by implicit premise that we are examining the behavior of a stable M/M/1 system under steady state or equilibrium condition so that the system throughput equals the arrival rate. Note that we use the symbol x naught to denote the system throughput here in order to be consistent with what is used to denote the system throughput, although it might be confused with the random variable x naught. Now we will calculate the average length for M/M/1 system. Now the average queue length, that is En sigma n, that is to keep the simple, we have omitted the lengthy mathematical derivations. Let next calculation average system time. That is ES is equal to En upon x naught is equal to 1 upon mu upon 1 minus rho. The result is straightforward with no complicated mathematical derivations involved. Note that 1 upon mu is simply the average service time, which measures the average time for customers for entering to departing the system when the system load is low. The average system time includes the system wait time when the system needs to wait for the availability of some system resources, but excluded the user wait time before entering the system. Now let calculate the average wait time. Average wait time, that is a W ES 1 minus mu upon 1 upon mu rho upon 1 minus rho. One can also get the average queue length in the queue alone, that is queue and which is by Little's law is equal to throughput mu p multiplied by the average wait time in the queue expressed as Since the purpose of this is to demonstrate how queuing systems are analyzed in the different ways. Now we discuss about the networks of queues. First of all, I am going to draw its block diagram. The output process from an M/M1 queue is a Poisson processes of the same rate lambda as the input. So far, now we will discuss about the independence approximation. That is clinic rock. Assume that service times are independent from queue to queue. Note a realistic assumption: the service time of a packet is determined by its length, which does not change from queue to queue. XP is the arrival rate of packets along path P. Let lambda ij is the arrival rate of packets to link ij. Lambda ij is equal to xp mu ij service rate on link ij. Assume all queues behave and as independent m/m/1 queues. So n is the average packet in network G. Average packet delay in network. So L is equal to sigma n ij. Ij is equal to lambda ij upon mu ij minus lambda ij. T is equal to n by lambda. Lambda is equal to xp, total external arrival rate. Total external arrival rate. Approximation is not good always, but is useful when accuracy of prediction is not critical. Relative performance but not actual performance matter. For example, topology design. Next is the slow truck effect. Short packet, large packet. Example of bunching from slow truck effect. Long packets require long service at each node. Shorter packets catch up with the long packets, similar to phenomenon that we experience on the roads. Slow car is followed by many faster cars because they catch up with it. Next, Jackson network. Independent external Poisson arrivals, independent exponential service time. Same job has independent service time at different queues. Independent routing of packets. When a packet leaves node, it goes to node next with probability p. Packet leaves system with probability, and packets can loop inside work. Arrival rate at node I lambda is I is equal to Ri plus sigma के lambda के pki external arrival external arrivals internal arrivals from other nodes. Set of equations can be solved to obtain unique lambda I. Service rate at node I will be is equal to lambda I. So far, external input, external input, internal inputs, customers are processed first. So far, customers exit with probability 1 minus p, customer return to queue with probability p. So far, when p is large, each external arrival is followed by a burst of internal arrivals. Arrivals to queues are not Poisson. Next, Jackson's theorem. We define the state of system to be n1, n2, ln k. Jackson's theorem I1 I is equal to k is equal to pi ni is equal to I1 I rho I n I1 rho I, where rho I lambda I upon rho I. That is, in steady state, the state of node Ni is independent of the state of the all other nodes. Independent m/m/1 queues. Surprising result given that arrivals to each queues are neither Poisson nor independent. Similar to Klein-Rock's independent approximation reversibility. Exogenous output are independent and Poissons. The state of entire system is independent of past exogenous departures. Thank you.